Every major industry relies on the mighty three-phase induction motor, but starting these machines is not as simple as flipping a switch, creates a massive electrical shock. This shock is known as high starting current and explosive surge. That can be 5 to 7 times the motor's normal power draw. This current surge stresses the motor windings, drops the voltage across the entire power line, and threatens the stability of the electrical grid. For decades, the simple engineering solution has been the motor starter, the ultimate challenge: how to gently wake up a giant without disrupting the entire system. The answer lies in precise control over voltage. Today, we decode the classic and robust solution, the star-delta starter. Three-phase induction motors are the workhorses of modern industry, but starting them is not as simple as flipping a switch. It requires a sophisticated solution. This solution is the motor starter. It protects the motor and the electrical grid from a dangerous phenomenon known as high starting current. To understand the need for a starter, we must first quickly recap how the induction motor works, specifically the electrical relationship between the stator and rotor. The induction motor operates due to transformer action. The stator acts as the primary coil, and the rotor bars act as the secondary coil. At the instant the motor starts, the rotor is stationary, meaning the magnetic flux cuts the rotor bars at the maximum possible rate. This massive rate of flux cut induces a huge opposing EMF and, consequently, an extremely high current in the rotor. This is where the problem begins. Because of the transformer coupling, the stator must also draw a proportionally huge current from the line, often 5 to 7 times the normal running current. This massive current surge can cause a dangerous voltage dip on the entire line, tripping circuit breakers and damaging other sensitive equipment in the factory. Therefore, the goal of any motor starting technique is simple: reduce the starting voltage applied to the stator coils, thus limiting the current surge. The star-delta starter is one of the most effective and widely used methods to achieve this controlled voltage reduction for medium to large motors. First, let's understand the two fundamental winding configurations: star-Y connection and delta-delta connection. In the star connection, the three N terminals U2, V2, W2 are joined together at a common neutral point. The input lines are connected to the start terminals U1, V1, W1. In the delta connection, the coils are connected end-to-end, forming a closed loop, where each input line is connected across one complete winding. The key difference is the voltage per coil. In a star connection, the voltage across each coil is reduced by a factor of 1 divided by the square root of 3 1/3. This deliberate voltage reduction reduces the starting current to about 1/3 of the current it would draw if started directly in the delta configuration. The star-delta method works in two phases: Phase 1, starting in star 4 controlled current, and Phase 2, running in delta for full power and speed. Achieving this automatic switching requires a complex arrangement of contactors and a timer, all housed within the starter panel. The starter uses three main contactors: the main contactor, the star contactor, and the delta contactor. Phase 1 star. When the motor starts, the main and star contactors close. The star contactor creates the short circuit at the end terminals, UDOs, UBADOs, doblido. With this connection, the motor starts gently, drawing the reduced current. The rotor begins to accelerate, converting electrical energy into mechanical speed. After a predetermined period, typically when the motor reaches about 80% of its full speed, the system must switch to the full power delta connection. Phase 2 delta. The star contactor opens first, creating a brief open transition, and then the delta contactor immediately closes. The motor is now running in delta. Each coil receives the full line voltage, achieving maximum power and reaching its final, stable operating speed. Crucially, the entire automated sequence is managed by a control circuit, which ensures the contactors switch at the exact moment determined by the timer. But a starter is not just about starting, it is also about protection. Every starter panel contains a thermal overload relay. The overload relay protects the motor from drawing excessive current for too long. This often happens if the mechanical load is too heavy or a phase is lost. If the current exceeds the safe limit, the heat buildup triggers the relay, opening the control circuit and instantly shutting down the motor. Additionally, A circuit breaker provides protection against short circuits, a much more catastrophic and instantaneous fault current. The final piece of protection is single-phasing protection, ensuring the motor does not continue to run on only 2 phases, which would rapidly destroy the windings. For smaller motors, a simpler and cheaper starter, called the direct online Dole starter, is used, where the motor is connected directly to the full line voltage. Dole starters are only viable for low-power motors, where the high starting current is small enough not to destabilize the electrical system. This is why, for heavy industrial applications like large pumps or conveyors, the reduced current of the star-delta starter remains essential. While modern variable frequency drives VFDs offer even better control, the star-delta starter provides a robust, efficient, and cost-effective solution for reducing electrical shock. The starting sequence is a critical engineering challenge. Mastered by the star-delta method, it allows massive machinery to start safely without crippling the grid. If this deep dive into motor starting technology helped you, please like the video and share it with your fellow engineers. Subscribe to UA Electric for more essential 3D breakdowns of the systems that power our world.